Hello everyone, and Happy New Year to you all. Thank you for joining us on our first webinar, NanoFrazor webinar of 2025. We're very happy to welcome Berke Erbas with us today. He's a doctoral student at EPFL with Professor Jürgen's group, and they were both very close collaborators of ours and super users of the NanoFrazor tool. So before I hand over the mic to Berke, I would like to give you a very brief overview of our latest innovations here at Heidelberg Instruments Nano. I have a few slides to go over the next generation NanoFrazor that we've launched this year. And before doing that, I also want to remind you that this webinar session is being recorded. So you may leave your cameras off throughout the official webinar time and the Q&A session at the very end. You can ask your questions to Berke directly. We will unmute the participants who have questions for Berke. And the Q&A session itself will not be recorded as part of the webinar. So you may feel free to ask any question that comes to your mind and also to turn your camera back on for a better collaboration. Great, so back to the NanoFrazor. First, let me introduce myself. My name is Jana Chaaban, and I'm the Head of Process and Applications Laboratory here in Heidelberg Instruments Nano. In the next couple slides, I'll be giving a brief overview of our latest innovation this year, the next generation NanoFrazor system that we've released recently. So what is the NanoFrazor technology? It's a direct write thermal scanning probe nanoelectronics method. It has its origins from IBM research, in particular from the IBM Millipede project that ran over a long time at IBM Research in Zurich. And the NanoFrazor has been commercial since 2014, so 10 years now, initially under the Swiss Litho AG name, which was our spin-off name from IBM. Later on, we joined Heidelberg Instruments in 2018, and at the moment we are about 25 employees based in Zurich, working on the development and the production of the NanoFrazor tool. Just this year, we launched our next generation NanoFrazor. It is highly modular, flexible to all your different application needs, and also 10 times faster with the introduction of our multi-tip that we call decapede, because it's 10 tips operating in parallel. So with the decapede, that's one way we're looking to tackle parallelization of our technology to have it have higher throughput and also higher reliability. For instance, if one tip was to fail, you can easily switch to the other tip and continue on your processing and patterning. And these tips are fabricated at the wafer level, similarly to the single tip. We've also made improvements to our electronics. They are lower in noise, faster, and also highly scalable. And we've also fabricated or gone through a production round of different packaging for our decapede. So now they come pre-packaged in a PCB that you see here. And this makes the installation of tips onto the NanoFrazor much easier. So rather than using a tweezer, you may now simply use your hands and plug in and plug out, as you see in this video, the decapede tips. So how this looks like, as seen from the NanoFrazor software that I'm sure many of you are familiar with. On the right side, you see a glimpse of the optical microscope that we have integrated in our tools. You see all 10 tips working and writing at the same time on the substrate. And in this image here, you see a live view of the topography that is being built line by line. At the bottom, you see, as usual, the target depth of this topography and pattern, and also the red depth, and you see how well they're following each other. You'll soon recognize this portrait. It's, of course, Mona Lisa, written 10 times. And here, each tip is biased independently, so the reader and writer is independently controlled for each tip of this decapede array. And in this example, we're simply showing one image that is patterned 10 times by each tip. But the end goal of what we want to have and what we're working on at the moment is to have each tip pattern a completely different design, as you can see in this simulation here. So one tip can be writing a 2D design, another can be patterning a grayscale design, and all of this can be also working in parallel together with our integrated laser writer head. What's also special about our new systems is that they provide a lot more flexibility. So you could have a base system, and it's very modular in the sense that you could have a single tip working, or also the decapite module, or also the laser writer head. And you can upgrade as you go with your research, or you could have all modules working together with the same base system. We also have different NanoFrazor systems that we offer our customers. So we have the smallest one in footprint, the one on the left, the tabletop system, or the one that comes with a standalone housing for reduced noise and influence from the environment. Or you can also think of taking your entire NanoFrazor writing tool with the tip and the laser and have it embedded inside a glove box and have this be part of a larger cluster of tools. So if you just follow this QR code or go to the nanofrazor.com website, you can fill out a very quick survey with just a few questions based on your research and application requirements. And we will recommend the best system and best modules for your research. Or of course, you can just feel free to reach out to us. So we're very excited about this new development, and we're very happy to have Berke on board. He's our fourth speaker in this NanoFrazor webinar series. And I want to mention to everyone that all the previous webinars have been recorded and they are available on YouTube and also on Bilibili for watching. So today we're welcoming Berke, and next week, also on Tuesday, we're welcoming Yannick for another session on grayscale lithography, but this time on nanophotonics applications. For today, we're very happy to have Berke on board. He will be talking to us about his work on grayscale nanolithography, which he's conducting as part of his PhD at EPFL. And he will be focusing on nanoelectronics applications. So Berke, please go ahead. The floor is yours.
Thank you, Jana. It's great to be part of this webinar series, and thank you for inviting me to this talk. Hello, everyone, and thank you for taking the time to attend this webinar. As kindly introduced, my name is Berke Erbas. I'm PhD student here at EPFL in the Microsystems Laboratory, and today I will share some results from my ongoing PhD research on grayscale nanolithography, particularly how grayscale patterning of solid materials can be advanced, and how this high-resolution pattern can be useful in nanoelectronics. And let me open also my laser pointer. Okay, for this purpose, I will start by discussing recent developments in grayscale nanolithography with specific focus on thermal scanning probe and nanoimprint lithography techniques and their application for 2D materials. Here you see the visual graphics of 3 key processes as an overview of this talk. And in the first part, I will focus on grayscale nanopatterning of solid materials using combined thermal scanning probe lithography and dry etching. The second part will concentrate on replication of these grayscale nanotopographies on various substrates to upscale this high-resolution nanopattern. And lastly, I will discuss how these surfaces are integrated in nanoelectronic devices. So when we are talking about nanolithography, traditional nanolithography primarily focuses on downscaling, achieved through techniques like electron beam and extreme UV lithography. In contrast, Grayscale nanolithography is based on non-binary shapes with varying depth profiles, enabling novel functionalities in applications like optic and fluidics. And similarly, common techniques for achieving these grayscale patterns are electron beam and interference lithography. However, E-beam lithography is limited by electron scattering, offering resolution in the tens of nanometer, while interference lithography is constrained by diffraction. And in our research group, we mainly focus on thermal scanning probe lithography due to its extraordinary grayscale patterning capabilities. This approach uses a heated nanotip to locally sublimate the polymer surface, and with the same tip, we can write, so remove material, and read what is patterned instantaneously. And with this integrated feedback, we can achieve sub-nanometer depth control, allowing us to pattern grayscale structures. And TSPL offer lateral resolution below 10 nanometer, 1 nanometer precise depth control, and on the other hand, it eliminates the need for additional development steps by directly sublimating the thermally sensitive resist. Furthermore, being both electron-free and charge-free, this technique is ideal for patterning on sensitive devices like 2D material-based devices. Unfortunately, despite these advantages, challenges remain. First of all, the resolution depends on tip diameter and thermal spreading, which can consequently impact the written feature size and repeatability as well. Additionally, the maximum patterning depth for high-resolution grayscale pattern is typically limited to below 100 nanometer because of the tip geometry and the polymer's thermomechanical response. And as demonstrated in our experiments, sub-10 nanometer features are only achievable within a few nanometer depths. And lastly, despite having similar speed to E-beam lithography in a few micrometer range, TSPL faces limitations in scalability because of the mechanical movement across large surfaces. And in our research, we focus on overcoming these challenges. First, we address the patterning depth limits. So we pattern ultra-high resolution binary and grayscale nanostructures with depths of up to 30 nanometer in general using a heated nanotip. Then subsequently, these shallow polymer depths are amplified during the transfer process into a SiO2 layer as a dielectric material, thanks to the significant difference in etch rate between SiO2 and the polymer. And this difference between the etch rates leads to anisotropic amplification of nanopattern depths. And this amplification process is illustrated here. However, the image you see here is not to scale. So on the left side, you see the top and the tilted view of this thermal probe, commercially available from Heidelberg Instruments. And on the right side, you see more realistic dimensions for the tip and nanopatterns. So when the micro cantilever, its nano-sized tips and schematics are shown at this similar or same scale, the impact of tip geometry on writing resolution can be observed more effectively. So for example, patterning at peak-to-peak depths larger than 30 nanometer significantly reduces the lateral resolution due to tip's conical geometry, basically. And for deeper indentation, in addition to tip apex, the slope of the tip, as you can see here, slope of the tip also play a role in the heat transfer, therefore preventing the fabrication of closed space pattern and limiting the aspect ratio of the fabricated nanostructures, or at least in the written nanostructures in thermally sensitive resins. However, with step amplification during plasma transfer, as I mentioned earlier, we overcome this limitation and reach higher aspect ratio grayscale pattern that standard tip cannot achieve. As you can see here, we can reach much higher depths than the tip size. And now I will share some of the details about the plasma etching step, which is the third step in this process flow. First of all, during this plasma etch, the gas composition, flow rate, and pressure are the critical parameters for achieving smooth etching and optimal depth amplification. Particularly pressure control, as you can see in the left graph, is critical for achieving trade-off between the physical and chemical etching, which directly affects the amplification rate. And on the other hand, the RF bias power applied to the substrate is the most efficient parameter in controlling the amplification rates, allowing us up to tenfold increase in depth. Beyond these parameters, we have also implemented a cycle dry etching process. This cycle process alternates between plasma etching and cooling cycles to prevent the substrate from overheating. And precise temperature control is really crucial for maintaining the sidewall protection on any grayscale or binary shapes, which allow for higher anisotropic amplifications. So only vertically amplify and the sidewalls are protected at relatively lower temperatures. And by benefiting that, we found that incorporating 5 minutes of cooling cycles between 100 seconds of plasma etching cycle effectively mitigates the overheating issues and improving the amplification of the pattern transfer, and it's make the process much more repeatable. So independent on the how much time you put in the plasma etching, if you divide 200 seconds of plasma cycles and you use, if you prevent the substrate from overheating, you can get more repeatable amplifications. And as a result, with this optimized plasma process introduced in the last couple of slides, we amplify shallow polymer patterns written on thermally sensitive resins. We amplify polymer patterns into SiO2, as seen in these figures. Sinusoidal nanopattern, as you can see here, are amplified in depth 5 times in this example, while preserving the same sinusoidal periodicity. And as we observe here in this comparison, we achieve amplification without any shape distortion, and there is no additional surface roughness introduced during the plasma etching process. So with our optimized etch process, we succeed in keeping the depth amplification to roughness increase ratio close to 1, mostly over 0.9. And this means that the transfer is achieved without proportionally increasing the surface roughness. So finally, we can conclude that we amplify only the depths vertically, but we don't introduce any roughness, extra roughness from the plasma process itself. Another important achievement is the quality of the transfer nanopattern. For this purpose, a Fourier transform of the measured AFM topographies is performed to characterize the sinusoidal nature of the fabricated nanopattern. And as you can see here, the polymer patterns are successfully amplified up to 5 times without any shape distortion. And this is further confirmed by second harmonic component, which is only 3% of the main Fourier component. However, at amplifications exceeding 5 times, we begin to see deformation of the sine waves and resembling mostly U shape at 10 times amplification. So when we are patterning and designing our patterns, this effect must be considered, particularly when aiming for higher amplifications. With this approach, any arbitrary shape like both binary and grayscale nanopattern, specifically rectangle and sinusoidal nanopattern in our case, are changing aspect ratio as a result of plasma etching process. So it's not limited to one specific design. Any arbitrary shapes are able to be amplified during this plasma transfer. And now let's have a cross-sectional view from the here to much more visualize what we have. So here you see a tilted cross-sectional SEM image, and the array of interest, grayscale SiO2, is first of all protected by a deposited carbon layer and then milled by focus ion beam. And in this specific case, sinusoidal nanopattern in SiO2 with 400 nanometer pitch and 150 nanometer depth are fabricated free of shape distortion after 5 times depth amplification during the plasma dry etching. As mentioned earlier, the limited throughput of scanning probe-based fabrication is a significant bottleneck for this technique. And despite comparable speeds to electron beam lithography at micrometer scale, it is unfortunately not suitable for now for wafer scale patterning due to the need for coarse mechanical movement outside of the piezo scanner range. And to address this challenge, we use grayscale pattern substrate as the nano-imprint lithography stems to enable upscaling through replication, particularly by step and repeat process on large surfaces. Therefore, we can replicate our grayscale surfaces on large wafers many times. And here, for example, you see an ultra-high resolution grayscale stem fabricated using this method. And this sinusoidal nanopatterns were then replicated onto a polymer layer on a different substrate. And following this imprinting, a second dry etch transfer process was employed to transfer the pattern onto the final target substrate. And through this combined approach, we achieve large-scale replication of grayscale structures onto wafers. Here you see images of fabricated sinusoidal surfaces after replication with nano-imprint lithography on thermoplastic resist and second pattern transfer into SiO2. But as I told you, it's another substrate. Generally, it's on a wafer. In this case, sine shape have relatively higher depths, around 400 nanometer and 500 nanometer pitch. So it's mean that we have an aspect ratio of approximately 1, and we can achieve relatively higher depths with the amplification process during the plasma. And for the final pattern transfer from the resist, thermoplastic resist to SiO2 on the new substrate, the same plasma recipe is which is developed for PPA and SiO2, are also used in this case, and achieving the same amplification and roughness control. Therefore, we can conclude that the reported pattern amplification recipes are generic and applicable to various polymer dielectric stacks, regardless of the lithography technique used. And finally, these nano-imprint stamps can be used as many times as possible, but preferably with cleaning after every 4 to 5 times replication. And in the next step, I want to discuss how these grayscale surfaces can be useful. Previously, the successful implementation of grayscale nanopattern has been demonstrated. For example, for optical meta surfaces used as a diffraction gratings and nanofluidics in biological application. And in our research group, we mainly focus on electronic applications. So when we talk about electronics, particularly nanoelectronics, 2D materials are one of the most studied topics in this field, because this material inherently have exceptional properties, including sub-nanometer thickness, flexibility, transparency, tunable electrical and optical characteristic, and low power consumption in transistor configuration. And these properties make them highly promising for next generation electronics. However, there are certainly challenges that need to be addressed for their adaptation in consumer electronics. These challenges include scalable material growth, reproducibility, achieving high quality and uniformity in grown material, particularly in terms of the mobilities. And similar to successful implementation in commercialized silicon transistor, silicon MOSFETs, strain engineering has demonstrated its effectiveness in enhancing 2D semiconductor mobility as well, by simply reducing the scattering within the material. And this leads to significantly improve mobilities, making under the tensile strain, making 2D materials more attractive for nanoelectronics application. So to induce strain in 2D materials, several techniques have been used so far, and this includes integrated MEMS system, deep indentation, bending, stretching of flexible substrates, bulging devices, thermal expansion mismatch, straining on press structure substrate, as you can see in these cases. And among all of these techniques, strain on pre-pattern substrate has attracted significant interest due to its potential not only for achieving high strain, but also their scalable industry compatible integration possibilities. And in our research also, similar to other pre-pattern techniques, we also focus on press structure substrate, but with smooth grayscale surfaces to engineer mobilities in 2D material placed on top of them. And how do we do it? We use this presented grayscale nanosurfaces as a platform to induce tensile strain into the in these atomically thin materials transfer onto them. And local strain in these 2D materials, which is MOS2 in this case, are achieved by pressing them against a press structure substrates, and the material here is mechanically elongated during the pressing, and after the attachment of 2D materials to the surface by van der Waals forces, the polymer is dissolved and the surface is clean, and consequently tensile strain in this pattern area is obtained. And as it can be seen in this AFM and EDX characterization, the sinusoidal surfaces enable a conformal attachment of thin materials and mitigates issues like wrinkling, rupture, or freestanding regions. And in this way, we achieve a mechanically stable and improved dielectric semiconductor interface. To characterize strain, optical techniques like Raman spectroscopy is performed, and as intuitively expected, a higher aspect ratio of grayscale nanopattern results in higher tensile strain in the transfer material. And using Raman spectroscopy, we demonstrated up to 1% tensile strain in MOS2. And on the other hand, with tip-enhanced Raman spectroscopy, we analyze the strain distribution at the bottom, top, and the slope of this sinusoidal nanopattern. And as a result, we observe that grayscale surfaces provide more homogeneous strain distribution on pattern region, unlike sharply patterned structures like pillars or rough crested substrates. After the material transfer on these grayscale surfaces and introduction of strain in 2D materials, again it's MOS2 in this case, 2D materials is patterned to form a semiconductor channel. And finally, source and drain electrodes are deposited through the lift of metallization. And for strain transistors, we observe up to eightfold mobility enhancement compared to flats, so unstrained transistor, for around 1% tensile strain and reaching the mobilities of around 185. And for approximately for 0.6% strain, up to 5 times enhancement is achieved, which is directly correlated to the strain level induced within the material. In conclusion, we have fabricated relatively high depth grayscale dielectric nanostructures by combining thermal scaling probe lithography with dry etching, and we achieve up to 10-fold vertical depth amplification. So the reported H transfer and the pattern amplification approach is generic and applicable to various polymer dielectric stacks, regardless of the lithography techniques used. And to enhance the throughput, we utilize grayscale pattern substrate as a stamp to replicate patterns over the large surfaces. And finally, we demonstrated the application of this precise nanopattern for strain engineering in 2D semiconductors, in which deterministic local control of strain is achieved thanks to the high precision of thermal scaling probe lithography. And this strain approach resulted in improved FET mobilities in transistor configuration. Finally, I would like to acknowledge that we benefited from several grants during this project and use EPFL micro-nanofabrication center, the material characterization platform for measurements. And as listed here, we collaborated with several partners from EPFL and ETH Zurich for 2D material synthesis, strain characterization, and metrology as well. That's all. I will stop talking now and I will be happy to take questions.